Lineage is a visualization technique to analyze genealogies in a clinical context. The goal of our collaborators is to understand complex psychiatric conditions such as autism and suicide. These diseases are caused by a combination of genetics and environmental factors. Our collaborators study these diseases using rich data sets, including thousands of diagnostic codes, detailed clinical profiles, genetic data, and genealogies, with the ultimate goal of discovering genetic risk factors that can be used for diagnosis and treatment. In this project, we use a suicide dataset containing 118,000 individuals and 19,000 suicide cases from 550 families. Genealogies provide important context when studying these diseases. In this genealogical graph, squares represent males, circles represent females. A filled-in node indicates that a person has committed suicide. Our collaborators would like to be able to map many attributes onto this graph so that they can understand whether suicide co-occurs with other diseases or environmental factors. Unfortunately, current genealogy visualization tools cannot map more than a few attributes to the graph and don't scale well to the size of the data. Here is an example of such a family with 400 members. The primary phenotype is shown as filled in, and other attributes are shown as labels. These graphs are not suitable for exploration. To remedy this, we have developed Lineage. Lineage is designed for the interactive exploration of large genealogical graphs and associated clinical data. It has three main components. A selection panel on the left allows analysts to choose one or more families to analyze and to select the attributes to display. The genealogy view in the center displays the structure of the graph. And the tightly integrated table displays the attributes associated with the nodes in the graph. The fundamental idea behind Lineage is to take a graph, make it into a tree, and then lay the tree out so that the nodes are associated with a table. The genealogies we consider are rooted and directed, but do contain cycles. Here, node 7 is the end of a cycle. In order to remove this cycle, we duplicate the node. Once we have a cycle-free tree, we can linearize the tree, assigning a unique row to each node. With this linearized tree, we can associate a table of attributes as shown here. Each column represents an attribute for the node in that row. One drawback of assigning each node a separate row is that this tree now takes up more space. It turns out that we don't always need to see the attributes of all individuals. We typically want to see the complete structure of the graph, though. To achieve this, we aggregate the tree using a binary degree of interest function that ensures that the attributes of our nodes of interest, the suicide cases, remain visible at all times. We use two different methods. Attribute preserving aggregation, as shown here, assigns each node of interest its own row and aggregates the other nodes of each branch into a row. A more aggressive method is attribute hiding. With this approach, only the nodes of interest are assigned unique rows in the table. All the other nodes are hidden behind these nodes and are not represented in the table. To visualize aggregated families, we use an implicit encoding. Parents are placed to the left of a line, children to the right. The nodes colored in blue represent people who have the phenotype of interest, suicide in this case. Now it's time to take a tour of Lineage. Here we see a dataset of 10 families with increased numbers of suicides. We start by browsing families in the family selector. The family selector shows the available families, how large these families are, and how many people have committed suicide. We can expand the graph to see all the details about every person, but for larger families, this is likely to require scrolling. When we aggregate, every person of interest still has a row in the table, but other nodes must share rows. This is useful for comparing people of interest with their family while still providing a compact view. When we hide attributes again, only the people of interest are assigned rows in the table. This compact view makes it possible to view families with hundreds of members while still preserving both the attributes and the familial information about the suicide cases. We can also selectively expand or hide branches in the tree. The table view contains one column for each attribute available for this family. We use different visual encodings for different data types. Categories are shown as filled in rectangles. When we aggregate, categories are transformed into stacked bar charts. Numerical data is shown as dot plots, which is also well suited for aggregation. Text labels give context about the suicide cases. Users can sort on any given attribute, bringing the relevant people to the top of the table. When we sort the table, the association to the graph is lost. We reintroduce this with slope charts connecting the graph to the table. Clicking on rows highlight them, which makes it easier to trace it to the graph. When we find a phenotype of interest, we can add in other families to see whether they also contain similar individuals. Sometimes it can be helpful to dynamically redefine the phenotype of interest. We can select either categorical variables, such as depression, or ranges of numerical variables, such as an age range, as our phenotype of interest. Notice how the blue fill that indicates the POI changes. The updated POI can then be used to aggregate the tree again. A selected attribute can also be shown directly in the graph. We use color codes for categorical values and a small bar chart for numerical values. Using these approaches, our collaboration partners are looking to find robust phenotypes within and across families, which they can then use to run genetic tests. We hope you enjoyed our tour of Lineage. Thank you for watching our video.